Okay, so we will resume. We resume by considering the role of energy for magnetic fields. So the magnetic energy is defined as the integral. There is a half there. Sometimes there is no half, but in my case I have a half of volume M magnetic of B squared in this volume. This is magnetic energy, and remember, if we want to consider, as we will do, what I'm going to say is partially general, and then we will consider highly localized field lines on tubes, and then on knots and links. Before thinking of these localized systems, I'd like to say that in general, magnetic energy is not conserved. What is conserved in ideal MHD is total energy, which is the sum of kinetic energy and magnetic energy. So imagine that these structures, if we think of structures of flux tubes, are relaxing because of the Lorentz force. They are relaxing, they are going down in their tension, magnetic tension. And as rubber bands, they relax differently than rubber bands. They keep a constant flux. Flux is conserved during this relaxation. Relaxation means that their magnetic, total energy is conserved, magnetic energy diminishes because tension diminishes, and as it diminishes, there is some conversion into kinetic energy. It moves in the fluid. It moves in the fluid, and then if it is, suppose it is a circular toroidal distribution of magnetic field lines, it will shrink. The torus gets fatter and fatter and fatter. Why it gets fatter? Well, because flux is conserved. If it shrinks and flux is conserved, then the magnetic field lines will decrease in their length under the Lorentz force, but the flux has to be preserved, and so if it is preserved, it means that intensity decreases, has to increase the cross-section. So if we start with some thin tubes subject to this Lorentz force, the Lorentz force will induce a shrinking of this tube towards the center of curvature, and we end up with a situation where the hole in the torus will disappear. And then these are magnetic surfaces, because I said suppose the field lines are always parallel to this boundary, there is no flux through, so as they are here, they are also here, they are always tangent to the surface, and so we have this surface that touch itself. And there we have to stop to talk, because a magnetic surface that touch another magnetic surface develops singularities, and we are back to the first minutes of the first talk of this course. We don't know what to do with singularities. We need some mathematics, and we don't know how to tackle singularities. Similarly, if we don't do it, if we don't know how to do it in principles, can you imagine on a computer? It's the same thing. Now, of course, the presence of these singular sheets is very important, and is very important in many contexts, because you may infer the presence of new currents, new phenomena in astrophysics, blah, blah, blah. Okay, so this is the situation. So the situation is you consider this relaxation up to a point where the surfaces touch one another. At that point, the process may continue, of course. It may continue because field lines are still not zero length, so they will exert a force. But we don't know how to say how the process goes, how it develops further, because we have to deal with this tangential problem. So we stop there. So for us, the final end state of this relaxation process is this one. And we are aware of the fact that, of course, this relaxation process can continue further, but we don't know how to deal with mathematics. So this is, in time, the process we have in mind. So the Lorentz force acts on these systems. If the system is like this, i.e. no topology or trivial topology, there is no topology, it will shrink to the unknot, is an unknot, and this unknot is just the tight torus, is the fattest possible torus. This evolution is a relaxation of energy, relaxation of magnetic energy, and this is done under some assumptions, and the first assumption is that the volume of the magnetic system is conserved, and the second assumption is that the flux of the system is conserved by Alfvén's theorem. That means that this thing, the couple, will govern our relaxation. So it's a relaxation of volume-preserving flows and the flux-preserving flows. We call this signature of magnetic field. Okay, so we consider the relaxation under signature-preserving flows. All right. Well, yes, in my case, for simplicity, yes. Okay, so one easy result comes from applying what we call it now Arnold inequality, and is very simple, and is the following. We know that helicity, the magnetic helicity, is just the integral of A dot B in dV. And we apply first the Schwarz inequality to this system. Okay, so we apply the Schwarz inequality, and we have that this is just the integral of what? Of A squared dV plus the integral of B squared. I'm distracted by the fact that on my notes, I noted I spot a mistake, is a typo. There is a plus missing. Sorry for this. Plus, no, there is no plus. No, there is no plus. That's correct. Times B squared Schwarz inequality. That's correct. dV to a half. Okay? So this is Schwarz. Schwarz inequality. And then we have another inequality due to Poincaré, and this is the integral of B squared in dV greater than or equal to a constant q. I will put a q squared there for some reason. Integral of a squared in dv. Where, so this is Poincaré. Poincaré inequality. Okay, I didn't write anything on this q. Well, no, I can say, so q is a constant that depends, at the moment, we can say only that q is of the order of of a length to the minus 1, where L, typical length scale of the field, of the magnetic field. I should add Q depends on the geometry. On the geometry only. Okay? So it depends on the geometry of the field. We don't know really what it is in general. And this is the inequality. So we can couple Schwarz inequality with Poincaré inequality. And so we take this inequality in terms of A, and we substitute there, and we have another B contribution. And so we produce this, let me call it Arnold inequality. By stating that the integral of b squared dv is bounded from below by this quantity q squared times the mod of the helicity of Hn. So it means that if helicity is different from 0 for systems that have complexity in space, then the energy, this is, if you put a half here, this is energy. The energy depends on time, is anyway bounded from below by the amount of helicity you have. That doesn't mean necessarily that your field lines should be knotted or linked. It can be also valid for fields that are not knotted. We will use this inequality, but certainly, you see, energy is obviously bounded from below in the sense that is greater than 0. So the minimum is 0. If helicity is 0, is certainly that the case. And we know that if there is a system that has some structural complexity, for the moment we say just it has helicity different from 0, then this puts a constraint on the lower bound of magnetic energy. Remember, why we're talking about lower bound? Because there is a Lorentz force that acts on the fields that make them relaxing all the time. So the situation is now to prove that the relaxation of magnetic field is giving you energy that is always going down. And this is certainly a piece of work of Keith Moffat of 1985, I think. So I'm going to prove that through an idea that I find it very beautiful because it's simple. Simple ideas are extremely hard, and this is the gift of Keith. He has always very good, simple ideas, and it's rare. Okay, so theorem We call it magnetic relaxation under. So let's say magnetic relaxation. Magnetic relaxation under magnetic relaxation the magnetic energy MT is a monotonic decreasing function of time. You find this, what I'm going to tell you, in a number of papers. Certainly, I think is 1985, the origin of this approach, and then has been repeated in a nice paper, Nature paper, 1990. So the idea is, as I said, simple. We have to look at dm dt, right? And to see how it behaves. So this is, we go inside the derivative. There is a b squared. There is a b squared in the energy. So there is a half in my definition of magnetic energy at the beginning. So the 2 and the 2 cancel. And so we are left with the b times b dt in the volume of the magnetic field. And so now we use for this derivative, I didn't say it, but it's implicit. We use the transport theorem again, and assuming that there is no flux through the bounding surface, so that the divergence term disappears, etc., etc. That's why we are left with this derivative. Anyway, now we use Faraday's. dB dt equals the curl of u cross b. Okay, so is the integral on the magnetic domain b dot curl of u cross b in dV, and okay, so this is okay. We just play around with these symbols. We extract u from there, so we have a minus coming out. The integral of what? Of u is a triple product of u dot the curl of b cross b in the v. And now curl of b is Lorentz force. The curl of b is the Lorentz force, is the electric current. And so we can write this as an electric current contribution, integral of u dot product of j cross b. Okay. Right. Now we are at the stage where we consider the relaxation. And so you assume that there is an end state. Relaxation proceeds and up to a point, and then this point is maybe singularity is developed, so you cannot go farther. You say that at that point is like reaching a steady state. So just a moment before reaching the steady state, you think that you have a flow acting on the system, or the system acts according to a flow that is no longer dependent on the second derivatives in time, but is like velocity. It's no longer like acceleration. is velocity. This flow is a modified version of Navier-Stokes, so close to relaxed steady state. Navier, you use a modified version of Navier-Stokes dynamics, and these are called, they have a name, Darcy's equations. So you state that instead of having du dt, you have something proportional to u. So let's say kappa u. This plays the role of du dt. And then on the other side, you have, as usual, the contribution from the pressure plus the Lorentz force. Okay? So you replace du dt with this. Okay, so if this is the case,
Renzo,
yes?
you just replace du dt with a ku just because at the touching region,
That's right.
du dt is 0
That's right.
because it's steady.
That's right. We are very, very close to that stage. Plus, you are very close.
Why is proportional to
You use to model the almost steady case where accelerations are no longer important. Well, you certainly neglect changes in velocities, right? But you don't want to state that is a steady state yet.
Just like a Taylor expansion around.
That's right.
So keep the question linear term. Can you repeat?
Yeah, is like we may think of a Taylor expansion. You may think of replacing the second derivative with the first derivative, neglecting effects of the second derivative in time. The derivative of the velocity.
Yes, I'm also thinking about Taylor expansion, but how to get this result? Du dt is proportional to ku.
No, it's not a result. It's you think is an appropriate choice. But of course you can
Taylor expansion around?
Just
near the steady state.
In fluid mechanics, we have a stagnation flow. Exactly on the stagnation point, the velocity is 0. So not exactly on that point.
But nearby.
To that point, we can always do the Taylor expansion. The velocity there is a linear function of the coordinate. For example, like
But then it's not u.
Is not you?
Because he said it's a linear function with a coordinate instead of u. You now use a linear function of u, which is
you can transform the spatial coordinate to time.
anyway.
This is a law. You can check in hydrology. We can check in hydrology. Hydrology is used, Darcy's law.
Linear Taylor expansion in a functional space of u instead of space of coordinate. So it's a function in a function space of u. So that maybe I think it's reasonable somehow. Okay. Please go ahead.
So is that result of low Reynolds number flow.
Mm,
Reynolds number.
So you mean Stokes flow?
yes, it means Stokes flows.
Okay.
I don't remember, maybe, yeah.
But I have another question. How do you get that to be negative? Just the line above this dot. You do that this is decreasing, so the right-hand side should be negative. Why?
The negative,
J cross B.
this one,
Yes.
on this line,
Yes.
um,
The last guy.
if I didn't make any mistake, I wanted to have the U out here. I think is correct.
Suppose it's correct. Why is negative?
Because if you swap positions, you get a minus sign.
Yeah, but minus sign, why is negative? It could be
Negative. Maybe you just because you are doing some scalar triple product,
Yes.
and you just do some swapping
yes.
between cross.
But the value, I mean the final value, is it negative? It could be positive or negative, but the y is negative. Yeah. It's decreasing because the theorem says that it's a decreasing function.
That's right.
It must be negative.
That's right,
Why is negative? I don't get it.
because there is a minus at the end of the day. But
J could be J cross B could be positive or negative.
I see what you mean.
Not you.
Yeah.
It just means the integral
I see. I now understand what you're saying.
should be positive.
Why is negative?
You're going to see it.
Because
That
this is the work of the Lorentz force.
I know, but
Work along the velocity, the work along the Lorentz force.
I understand. But here too. So we are going to substitute this. So whatever is the result of the Lorentz force, it will be compensated. You understand? You're saying, what about the result of this can be negative or positive, if I understand correctly?
The work.
Yeah, the work's done. But you're going to, no, you're going to substitute that in there. So whatever it is.
Okay, you have not yet proved.
So, no, not yet. One line. No problem. So indeed, I need the condition somewhere before, I should have said, because you asked, div u 0. You know this. Okay, so we use this there. We use this there. And we have dm dt equal minus this k integral, the volume of the magnetic field, and then we are left with a u squared in dv. And that's why you have this negative sign that whatever is the result of J cross B holds. And because this is positive, then evidently this has to be a decreasing function of time. With time going to infinity. Okay. Remember, magnetic energy has to be positive anyway, greater than 0, so it has to relax down towards 0.
So here we use two assumptions. No, one assumption which is one is the Darcy's law. So I don't know why we should use Darcy's law, but anyway, how come the Poincaré inequality? Poincaré inequality. How come? Can we prove it?
Poincaré inequality, I do not remember if it was done. I can't remember the context.
It always involves the gauge.
Yes. Yes, my difficulty is that I don't remember which context it was done. So that would have helped me to justify it. So I I don't remember. It's a good question, actually. Did Poincaré... Certainly, I know some work of Poincaré, and I read through... he wrote a book on... He wrote a lot. You know, Poincaré is interesting. I'm now done. I cannot remember this, where it comes from, but I do remember that he used to give a course, and for a number of years, he changed the topic every year, completely. And out of the course was coming a volume. And so on each year on totally different topics. So there is one, of course, on celestial mechanics, and the following year maybe vortex dynamics, and then the following year on potential theory, and the following year, so it's amazing.
Okay, you mentioned potential.
Yeah.
Suppose here.
I know.
Omega.
Yeah.
A is 3, suppose. Let's
Yeah.
go.
And that would be wrong.
Maybe one way to prove that Poincaré inequality is to use Biot-Savart. Substitute Biot-Savart into...
Well, certainly, I bet, maybe I'm on record, so maybe I lose my bet. I bet it's not done through Biot-Savart, no. It might be done through functions in general, some relationship between functions.
A and B, you have relation. B equals
And you're saying, yeah, I know what you're saying.
B can be 0, A can be anything. So why is, if you write in the other way, A is greater than B squared, multiplied by something, I will be more happy, but I still don't understand why.
Maybe, well, there is a possibility of some mistakes in my notes. But no, but come on, let's see. We take this, A greater than. Yeah, that's correct. No, it works like that.
I'm curious.
But I don't know. I don't know the origin, and I don't know the justification of that. But I see what you mean in terms of velocity and vorticity.
Maybe Q will be 0.
Yes, that's the solution. That would solve the problem.
But we have to pay attention to the integral. So I have a suggestion. Maybe we can just recall our knowledge of particle physics or gauge theory. That is, think the B and A to be gauge field theory. Gauge
Right.
Field, tensor, and the gauge potential. Do we have an example in gauge theory for that one? The F square is bigger than A square, the integral. I don't know.
Good. I like the challenge.
Now I'm reading, now I'm reading gauge fields.
Okay. Well, thank you. Right. So we have a result that is related to this approach that I like to mention immediately, and opens, in a sense, opens the field. I mentioned Moffat 1990, and indeed this is the paper, Moffat 1990, and is a Nature paper. Is about the energy spectrum of knots and links. And pardon me?
Using this Darcy law,
Sorry?
this paper contains this result.
Yes. But as I said, this result is older. I might be wrong. Is much older. I think he wrote 2 papers on magnetic relaxation, 1985. Certainly that one I have in mind, and is a JFM paper, that one. So the theory goes back to these studies. And the result I'm mentioning now is the following. It relies on this, under signature preserving flow. The minimal magnetic energy M min of a field B. And now I consider for simplicity that B is in a flux tube and possibly forming a knot, is given by M min, given by some function M of H phi squared times volume to minus a third. Volume minus a third means 1 over L. Remember, Q depends on this L, on the size of our structure there. So if it is relaxed or not. And this M of H, where M of H is a positive, dimensionless function of the, let's say, dimensionless twist parameter H. So this result is based on dimensional analysis, is very, very simple. And I need to give you some idea about what I mentioned, what is the twist. So remember, we introduced the flux tube with a twist, or with twist, because we had the field lines that were twisting about the center line. In the decomposition I took was BM and BA. Axial BA and meridional BM. And so, very quickly, I'm going to remind you what is twist. So twist, one way to talk about the twist is to think of a cylinder and to refer everything to the center line of this cylinder. The center line, I will call it X, and there is an arc length on this, so that means that my X, my curve, my center line of the tube is given by this vector position. And then the twist is formed when a second line, I will call this second line X star, makes a turn about the center, okay? Like so. So you have a field line here, X, and the second curve, X star. And you think that X star is given by the first X plus a distance. It can be the thickness of the tube, or it can be within the tube. Let's take a small parameter epsilon compared to the scale of the tube, and epsilon, and then is in a normal direction. Okay, a unit normal. So you construct the second curve through the first one, right? And then you can define. So this n is one of these arrows here. You can think of n. You can define n. You know, you put the cylindrical polar coordinates there, and you can define n in that fashion. Say cos theta n, the unit normal of Frenet plus the sine theta be the binormal of Frenet, and there are many ways to construct this unit vector. So from elasticity, from 1900, from Lamb's book on elasticity, you have is Lamb book on elasticity? I can't remember. Well, there is certainly a Lamb on hydrodynamics, very famous book for me, and there is another one on elasticity that is famous. I'll check tomorrow, I'll tell you, but I think it's that one. At that time, you know, many compendium, many book, was a time where people like Maxwell were able to integrate what was known into a book, but of course it was a thick book. And from then, you know, a single chapter of that book developed into several books, so it's no longer possible. But there is a theory of elasticity, exactly as it is a book on the mathematical introduction to, etc. This is very famous. And there is a definition of twist there, and the twist can be defined according to that definition as 1 over 2 pi, the integral of this n. I'm now taking first derivative with respect to s. So this is the derivative with respect, I can explicit it. So you see dn ds along the line how n changes. And this is cross product with n. And all this is a rate of rotation. And the rate of rotation, we want to take care of the rate of rotation in this direction. So you have to multiply this vector by the unit tangent in this direction, t, to c, and you integrate this in S. You do some calculations here. You explicit n in terms of unit normal and binormal by Frenet frame. You substitute that here. You take your derivatives, and you use those equations, the Frenet-Serre equations I mentioned to you before, and you can show that this quantity is given by 1 over 2 pi, the integral of the torsion of C in ds, plus a certain quantity, let's call it a total jump in theta, if C is going to be closed over 2 pi. We call this quantity here, the first one, total torsion T, and this quantity here, intrinsic torsion, curly n. What's the difference? Well, the difference is, suppose you have no total torsion, suppose your tube is straight, you have a twist. Okay, you take your belt, you pull it tight, and you may have it twisted. So the twist can be 0 only if the two terms compensate with opposite values, right? So if you take a straight line for C, a straight tube, you may have twist, and you visualize twist very well, and that twist is called intrinsic twist. So T is total or normalized, because this is 2 pi there, normalized total torsion, and curly n is intrinsic twist. Okay? Imagine you have your ring made of field lines, and now imagine that these field lines are all twisted about in this toroidal configuration, and these field lines close on themselves, divergence of B0, but they have a twist inside. And imagine now that this torus, this one, is just a planar torus, so that the axis is a planar circle. Well, in that case, torsion is identically 0 everywhere, but you have field lines that are winding around the center line. So H here is related to what? Is related to this twist. Is related to this twist. And this twist has to be related to the ratio of these two terms. Because according to the fact that you have the meridional field large or small, you may have more twist or less twist. It's exactly like elastic bands. You twist up elastic band, you cut it, you take it tight, and then you twist it. And then something happens, right? You twist it, do this exercise. It's fun. You twist it, and then you release it. You relax it. And as you relax it, there is, under your eyes, a conversion of twist energy, of torsional energy, into something that biologists may call, well, it's not technically correct, but the word is very close to the correct one, is supercoils. DNA supercoils, because it relaxes high tension torsional energy into bending energy. We will talk about that tomorrow. It is a key feature of continuous deformation of systems. Anyway, so this H is related to the ratio of these two quantities. If you want to have an exact information about that, I just write it down for you. Because the field induces a force, also among the components of the force. So for the field somewhere, I don't know where I wrote it. Maybe I didn't write it. Okay, roughly this twist is more or less, because there are factors there, is just B theta contribution in Bm over Ba or Bs. I call it before. The functions that are inside there. Okay, so the H is basically the twist. There is a 2 pi and etc. So we want to find out more about these things. So we want to say something about the energy of knots. And something about this function, m of h. You understand that m of h, we want to find out m of h, because this is left undetermined in the paper. And we understand that if h increases, if we put more twist, the energy increases. I gave you before the other example, the example where you put a lot of twist and then you relax it. You have your fingers pulling tight a band, and then you relax the energy by just letting the band shrink. And as it shrinks, relaxed energy converts the twist into the writhe. Okay, so we want to find out more about MH. But now I'm coupling the two things. We are at the right time to couple the two things. First, what about if this is not just a simple unknot, but is a knot? Is a knot. So let's finally try to draw a knot. I'm very bad at this. Can you help me? Okay, so maybe something like this. Looks like a knot. I have to do it properly. I never succeed. I have to draw carefully. Okay. How is the knot? Trefoil knot. I have to look at the picture. You know, I've done it so many times, and all the times I'm in trouble. Do we have a trefoil knot somewhere? 66. But it's 66. I don't have it. Oh, yes, it's here. Oh, you have 66. How is possible? I don't have 66. You have more notes than what I got. Okay, yes, I like this picture indeed. I wanted to draw this picture. You know, the experts on knots, like Kaufman, is able to draw whatever knot you ask him. He starts drawing, and he has in mind exactly. And I cannot even draw a trefoil knot. But I'm in good company because I met people famous topologists who have the same problem, so I feel happy. All right, so this is, okay, like this, and this, we want something like this, and this like this. And imagine that this is your trefoil knot. And is what you may call it a loose knot. But now we put magnetic field in it. So a magnetic field, we know what it's going to do. It is going to relax. So under relaxation, this thing, and I will attempt to write what I want, like this. Without the help of this drawing, I wouldn't be able to do it. Like this, and then like this, and then what? Maybe like this, and like this. You understand what I'm saying, what I'm doing? And then here, well, just to close up. It's very hard I'm very bad. You know, one thing I can say is that once, many years ago, Keith came to me and said, "Wonderful, you do wonderful drawings, Renzo. You must be very good at drawing." And I'm very bad at drawing, as you can see. And I just pay attention, just sit down, and I spend time until I'm happy. So I'm very, very bad. But anyway, this is it. So this is the relaxation under volume-preserving diffeomorphisms and under volume and flux-preserving diffeomorphisms. So we have flux is conserved, but the whole knot stretches and gets smaller and smaller in length. That means that the average cross-section increases until, if there is some topology, then the relaxation gets you to an end state. And this end state, the minimum energy, has to be a function of the topology. Why? Because if I start with a knot that is more complicated than this, for example, I just put an extra link in that, this will determine here. Of course, it will be fattening as well, you know. It will be fattening as well. Somehow it will be squeezed by the other, maybe in between there, right? Like so, more or less. That means that this stage is not the same as the other one, because we have more complexity in the field. More complexity in the field means that what determines the complexity that is invariant of shape is geometry, is topology. And being topology is, you expect that topology dictates the end state of the energy. We know that the energy has to go down. We know that it has to stop somewhere greater than 0. We know also that it depends from the relationship M min equal H mH times quantities that are constant. There's a flux square volume minus a third. That this function has to be function of the topology. But as you see, there is an H here. And also the H is consistent with our intuition, because H means if we put a lot of twist in it, energy still increases. So we think that maybe the minimum state is the one for the function m of h when h is 0. H is 0, 0, twist, so to speak, because twist is the sum of intrinsic twist and torsion. So it's more complicated than just thinking that the field lines go parallel all around, because if the structure is twisted in space but is relaxed, is the sum of the total torsion plus the intrinsic twist that has to go down. And if this is consistent with what we think, then evidently this function has to have a minimum. And at h equals 0, this function will probably have a minimum that is the minimum of the magnetic energy for the topologically complex state. Okay, may I keep it for... odd enough, I don't have... Oh, okay, it doesn't matter. Oh, it's okay.
So Renzo, I
Yes,
have a question.
yes.
So can I just have the following understanding? If that picture,
Yes,
that one,
yeah,
before the relaxation, on this strand, for each small piece of strand, it is highly twisted. Then the result will be different.
correct.
For that one, for that thick one.
Yes. Yes, I am happy to comment on this because it's also part of a little of my work. So, you know, we have a whole bunch of new problems, first statement. You may say, you know, we started thinking of a flux tube without any structure inside, without any complexity inside. Field lines, almost the flux tube was full of magnetic fields, but we didn't care that much. And now we move to caring. To start caring, we're saying, okay, there is a twist inside, the field lines are decomposed along a meridional and an axial component. Somebody will come up and saying, okay, there is no external flux, but maybe internally there is a rearrangement. Some other will come and say one day, the tube is exactly what you say, but inside there are particles moving, and it's chaotic inside. And these field lines are not closing on themselves. And all sorts of more complicated approach. Just to stick to your question, the answer to your question is, yes, for example, if we have a magnetic, we assume that the axial component is dominant on the meridional component. Because we want to think, we started from a bundle of field line, and then we put a twist, and now we're moving to consider twist and the action of twist. But once we have twist, we may say maybe the meridional component gets very strong at a certain point. So it confines the axial component. Yes, you may have this situation. Of course, I went to the extreme of your question. The question is, you may have a localization of twist that are enforcing the energy to relax in another direction or to limit the fundamental state of energy. And this is absolutely true. Absolutely. It opens up many, many problems according to what you like more and what is consistent with nature or what you investigate. For example, we will learn tomorrow that is not so far away from what we are already saying, because the question behind the question is a story of measuring complexity internally. And measuring complexity internally means linking numbers. We will introduce linking number, and there are higher order linking numbers, and there are higher order of degrees of complexity inside. Yeah. So the simplest example I can offer you is thinking of this flux tube the other way, not the way I do it, but the way that a flux tube has a meridional component extremely strong. Then it squeezes, it relaxes in another sense. And it may stop this process because we assume here, you see, that this is the main contribution. If this is the main contribution, then of course we have a Lorentz force that is acting inside. Okay, so the question now is to work out this M of H and to do some work there. Let me change for a moment. I want to keep going with this, M of H, but before going there, I'd like to say this. I need, again, a piece of paper because I have to copy the pictures. There are a number of issues here. As I said at the beginning, the field is exploding because of so many interests. One aspect is the following. Lorentz force acts along the normal principle. Curvature times the principal normal. Okay, so if you have a field line in the plane, like this, okay, this is a field line, then the principal normal is in this direction, so the Lorentz force acts in this direction, and the principal normal is in this direction, at this point, in the opposite direction. Indeed, here, there is a point where you call it curvature equals 0. You call it inflection point. Inflection. And an inflection point in the plane is just easily identified by a change of concavity. Now, suppose you go somewhere, and this is now your field line in space. In space. You say, oh, well, why then? You talked about the plane, and now you talk in space. In space, I'm not so sure if there is an inflection point there. No, you have to be sure. Why? Because curvature equals 0 is an intrinsic information. It does not depend on the projection. Of course, I can project the curve that it has apparently no inflection points, but the curve, if there is a change of concavity, in other words, if intrinsically curvature is 0 somewhere, then there is an inflection point. If there is an inflection point, the Lorentz force will rearrange the curve. Why? Because the Lorentz force doesn't like to have these two concavities nearby. How you prove it? Well, is a piece of work I did. You prove it because you have to consider the steady case and the generic inflectional geometry for the axis of the tube, and then you check on the curl of the Lorentz force. I don't want to drag you in that. There's a lot of calculations. But the curl of F, it gives you the information that F changes, rotates around this curve. So you Taylor expand the curve around the point C equals 0. And so you find from this Taylor expansion, you find a generic inflectional geometry. It means that you have a piece of curve, a piece of your Taylor expand around this geometrically. So you have a piece of curve that is giving you inflectional geometry, and then you impose this curve to be a field line. You calculate your Lorentz force on this inflectional state. Maybe you want to be more sophisticated than that, and you consider a tube with the twist, etc., etc. And then you can prove that the end result is for magnetic fields, you have inflectional disequilibrium. Now I want to show you something. Inflectional disequilibrium means that the field lines do not keep this inflectional state. They get rid of the inflectional state. It's very easy to observe this phenomenon if you play with harmonic wires. A thin wire that is highly elastic, and you try to twist it in order to have an inflectional point. So you buy or you get a little very thin bar that is relaxed straight and has no twist, mechanical twist in it. And then you try to move it to have an inflectional point. Of course, the straight filament, the straight bar, is a continuum of inflectional states. But you want to have an inflectional point that is localized at a single element of this. And then you see that it doesn't stay like that. Now, for knots, you have knots that may have inflections. And if these knots are made of magnetic field lines, they don't like to stay with inflection points. So they get rid of inflection points. They rearrange themselves during relaxation. So I want to give you an example of that, because this leads me to show you something that is physically interesting. So you have a good picture taken from one of the famous books on topology to illustrate this. I'll try to very quickly to draw it. So suppose, I need some of your time. This is a figure of 8 knot. You understand why? Because it looks like an 8. Okay? Right? I should put more thickness here just to emphasize the fact that it is really a physical knot. Okay? And this knot is a figure of 8. Each knot, well, this is no time to talk about fundamentals of topology, but at least something intuitive I can say. For example, that one way to classify complexity in topology is to look at the minimum number of crossings that you have. But of course, this minimum number, by definition, minimum number is minimal, but these crossings, of course, can be any number you like, because I can take this strand and I can do like this. So you see, I have one more crossing. It looks 1, 2, 3, 4, 5 crossing knot. But this, you understand very well, that can be reduced, removed by a twist move. And if I do a twist move to this, I get this. If I do a twist move on that, I introduce twist. If I had twist inside and I twisted in the opposite direction, I remove twist. So this adds to the complexity of the problem. Anyway, you count the minimal number of crossings you count is a crossing number of the knot. And this is, of course, being a minimal topological invariant of the knot type. You can classify knots according to the crossings, for instance. So you can go up how many you count. So Tate did this work with Kelvin, because Kelvin, I told you at the very beginning, he wanted to have a kind of table of vortex atoms, and he said, well, he knew from chemists already that energy had to be discretized, and so he asked Tate, much younger, but a good friend, and they stayed friends until life. Actually, Kelvin passed away, Tate passed away, and Kelvin, very sadly, wrote an obituary for the younger Tate. Kelvin had a very long life. He passed away in more or less the discovery of the electron, 1905. Anyway, so he asked Tate, the one who invented the indentation on the golf ball. You know, the golf ball? Golf is not exactly a spherical ball, it's a ball with some indentations. And this indentation made in the surface of the golf ball were invented by Tate, because Tate was a very keen golfer, and Kelvin was a keen golfer. And very interesting, Kelvin, you think, oh, okay, Tate went to visit Kelvin regularly. No, it's the other way around. For some reason, Kelvin, the senior professor, used to go all possible weekends from Glasgow to Edinburgh to visit Tate to play golf together. And Tate invented this indentation in the ball to have higher lift, so to speak. Very interesting. Anyway, and so he asked Tate, very young, he got a chair in mathematical physics, much younger than Maxwell. They were at school together, Tate and Maxwell. Tate and Maxwell were at school together, schoolmates. And then when Maxwell went to Cambridge, so they had the same age, but when Maxwell went to Cambridge, Tate was already his tutor. So the first years, Tate was excellent, and Maxwell was a little bit behind. But at the age of 21, Tate has a letter to him, to his good friends, and he said, I can see you are now blooming. The age of 21. So he had as tutor, he had Tate in Cambridge. Anyway, Tate was a chair of mathematical physics in Edinburgh, and so Kelvin asked Tate to tabulate knots, to study knots, And how do you identify a knot with another one, etc. So that's the origin of Tate tabulation. And so we have a 3-crossing knot, the trefoil I drew before, and then the 4-crossing knot, which is this one, 5-crossing knot, 6-crossing knots, etc. And as you increase complexity in this knotting, the number of knots with the same crossing number, here 4, but different knot type, are exponentially increasing. So for the trefoil, we have only 1. For the 4-crossing knot, we have only this one, so I'm happy. 5-crossing knot, we have already 2 different knots that cannot convert continuous deformation, one into the other. So Tate was happy, and was happy with the 6-crossing. We have three different types of 6-crossing knots, and then I can't remember how many 7-crossing knots. I used to know all these things. You know, I'm aging. I'm getting old and old. I forget things. But anyway, so this goes up quickly. For 7-crossing, I don't know, 21, and for 8-crossing, already several more, and it goes exponentially increasing. Yeah, exponential. So now if you wonder how many knots have been tabulated, studied, there was a paper in the Notices, the American Math Society, at least 10 or 15 years ago. They were tabulated with a computer, of course, one more or less 2 million knots. And I'm absolutely out of date with this information. So you go on internet and you check and you will find out. Now there are ways to tabulate, to check on knots, if a single knot is different from the other one. And in order to check that, you need tools. And one of these tools, we have many tools, and people are in search for the final tool, but it will be forever, probably. And one of the tools, here we have a tool. We count the crossings. And if a knot has 6 crossings and not less, is different than this one. So this is the tool. And more than a crossing number, well, maybe linking number. Tomorrow we talk about linking number. And then linking number, even linking number is not enough, so we have to introduce polynomial for knots. And the knot polynomials remind me of the Fields Medal of Jones, 1984, so we are pretty close to now these years. Knot polynomials is not enough. And the story repeats. We need big homological theories. So we have Kovanov homology and other homologies, Lee and many others. And these theories try to capture the essence of these tabulations and this complexity. But being an infinite number of knots, I think we'll need an infinite amount of time. And so there is no time left, and I have to move. And so let's consider this, and let's consider, sure.
Does the polynomial grows exponentially with the order?
Do you know, Shin? If this is an interesting, I don't know. I think is known. The degree of the polynomial of any Humphrey PT increases exponentially with the exponential increase of the complexity of the knot type, of the crossing number? I'm not sure.
But it should be a finite number of terms.
So if it's not, then polynomial is not enough to describe that.
Oh, it's certainly not enough.
It's certainly not.
No, it's certainly not enough. We know that.
So we need more powerful tools.
Sure. This is the reason why, they say, knot theorist is one of the things I learned at the beginning. Say, you get depressed, oh, don't talk to knot theorist. Knot theorist is a famous blue, the blue of a knot theorist. Because at the beginning, Tate, for example, you see here, is if we put orientation, we usually do because we think of field lines, it goes under, over, under, right? And so you tabulate knots, and all these knots up to, I don't remember now, 8 crossings. 8 crossings is already a number of knots. They're all alternating. And so he was very happy. He was very happy after several years, he published a paper, very happy, and he submitted the paper, and during submission, he discovered the first non-alternating knots. Because he thought, intuitively, as everybody, we think, well, maybe there is a sine, cosine going on in this parametrization. Who knows? Up, down, up, down, up, down. But then he found non-alternating knots. He was depressed. So for several years, he stopped, and then he worked again. He went on for 20 plus years. But when the first depression told Kelvin, no hope. He said that this is terrible. I thought to be close to classification of knots. No, they are far more complex than that. But nature is not that complex. So Kelvin had hopes until 1880. More. And okay, we have a 4-crossing knot. I should a bit speed up here because I want to modify this knot. I want to introduce some changes in the shape. So I will go like this. I do a little twist here, and then something like this, and like this. Like this. Sorry. Even with the drawing, I cannot draw properly. Then this. Then this. Okay. So I'll show you. I need to go through this stage to show you what I want to do. Okay. Okay, so we do this, right? We take this and we twist this part, right? This is called Rider-Master Type 1 move. We can call it a twist move. Nothing changes in terms of topology. It changes in terms of geometry. And now we lower this part inside here, okay? We lower that part. And then there is something that, trust me, you will see. The picture is too long to draw, but after doing this and rearranging strands, we can rearrange the same knot in this fashion. Oops. No, I should stop here. And I go like this. Then I go like this. And like this. Okay. Is the same knot, and by the way, 1, 2, 3, 4 is the same crossings. So same knot, same crossings, different geometry. What's the difference between this and this? Because if this is rather thin, this may have inflection points, but this has no inflection points, especially if you think that it's drawn close to the plane. But it can be drawn also on a sphere, this one, because of the symmetry of the knot. It stays almost on a sphere. Of course, its thickness means that it is not lying exactly on the sphere. It has ups and downs with respect to the surface of the sphere. Now, why I'm interested about this? Because there is an inflectional instability if this is a magnetic knot. And if it is a magnetic knot, it cannot stay in this shape, but it takes this shape. Okay, now I'm almost done with my proof. This is not a serious mathematical proof. But suppose that this is the surface of the sun, and these are flux ropes, are plasma loops. And you have a picture in your notes, and these plasma loops are show no inflectional stage. But you have also another picture taken from the same mission, TRACE satellite, that show a destabilization of a magnetic rope when there is such a thing. When there is, at a certain point, a twist move. Now, the twist move is the result of an inflectional instability. So, there is evidently some twist, an excess of twist. We call it kink instability. If there is an excess of twist above a certain threshold, is kink unstable, it can break up. But if it is enough to rearrange, it will rearrange. It will rearrange, and what you see in pictures is whatever is the complexity. Of course, you have much more than this. You have the solar surface, something like this, and you have your braid pattern here forming, okay? Some braids like this, and field lines are captured by photospheric motion, and the photospheric motion introduce mechanical twist in these field lines. The field lines absorb twist from the photosphere, and it gets channeled in these field lines, and up to a certain amount. When it's above a certain amount, they break up. And when they break up, because it's too much, then immediately is like, an elastic system. They open up immediately like this, flip out, and they release a lot of energy. And this is the mechanism through which one of the mechanisms through which we receive energy from the sun. And this happens every second. Every second. You go on internet, you check, and you see the events, and some of these events are enormously catastrophic. So I'm sorry to take your time, but it's interesting to know that these events are now object of intense research from many viewpoints, and one I like to give you is the one that young people like most probably, is the fact that imagine that this event, one was in 1947, lasts a minute, imagine. These events last seconds, 15, 20 seconds, 30 seconds at last, but imagine that is a very long time. Now, these events are such that annihilate, so to speak, the satellite used for telecommunication. So they would block telecommunication completely. So now telecommunication is so important and crucial that what you do is, the simplest thing you can do is just to send many satellites and backing up one another in the hope that if for some reason one failed, there is another one that assists you. And I was invited 2 years ago in Sweden, and the government of Sweden wanted to have some experts to tackle the problem of big crisis in telecommunication, in energy supply. Very interesting, because these phenomena do not kill, so to speak, big power station or power grids. They kill the big power grids that have some supply, but they kill also the network, the small apparatus. And there is no enough trained people to be sent off to reset the apparatus. The big apparatus are automatically reset, and they keep going for some time with some extra fuel, some other form of energy. But the small apparatuses, this is the problem. The grid serving very small villages around, there is not enough people that physically have to go there to reset the apparatus. And the Swedish government said this is a very big problem for Europe. All because Europe is lots of small villages around, distributed, etc. And at the time of a crisis, we can reset the big grid power system. But the small ones need thousands of people to go around in a car one day to reset these apparatuses, because many of them have to be reset manually. And so they said, this can last 4 days, 5 days. And 5 days of blackout means hospitals are in crisis. Big hospital, I mean, many systems are critical. So I attended a very interesting meeting when people very far from my expertise went on and they talked about the effects of the solar activity and these effects. The solar eruption may cause to Europe. So they are very seriously thinking to put money for this thing, not only for just cell phones. Okay, I wonder, should I stop here? Okay, so I'm not done. This is just to tell you that is a way to prove that through inflectional disequilibrium, you go from inflectional knot to inflection-free knots, and these, you may call this type of knots, the ones in this form, closed braid. Closed braid is another word for a knot. A knot like this is a minimum number of crossing knots. Some knots, all knots can be transformed, can be deformed into a closed braid configuration, but sometimes you want to have information about minimum crossing number, and this minimum crossing number in the closed braid representation is not conserved anymore, it increases. So the business is, first of all, we are now established the fact that through the Lorentz force, magnetic knots don't like inflections. Now we put aside this issue and we focus on M of H. M of H, the spectrum of M of H when we go to minimal energy, setting twist 0 for simplicity, and finding something about M, and how energy increases with knot complexity increasing. Okay, we're relaxing something that is more and more complex. Say a knot, a simple knot, a 3-crossing knot, a 4-crossing knot, a 5-crossing knot. We expect that the crossing number has an influence on this minimum energy state. So that would be for tomorrow, and tomorrow we'll talk, of course, about helicity and linking numbers, because this is an important issue, so I cannot miss it. All right, we stop here. Sorry that I've been bifurcating in many directions.